This is part 2 of my IoT security presentation. This is the smart parking lot breaking and fixing section. So let's start off with a bit of a review of the first presentation. So recall that the motivation for this project was Bowerly Road Lot 1, that large parking lot in front of the new engineering building, which, as you will most certainly know, quite often has one or two empty spots in it, but you're never quite sure whether there are actually any empty spots. And so I found myself quite often driving around the parking lot looking for a spot that I wasn't sure if it was there or not. And so this parking lot tracking system would enable you to know, are there any spots green? So some of the goals for this project were to do it with only a few sensors and to collect as little data as possible. That second goal especially will help reduce the impacts of some of these attacks on the system. And then, of course, the design of the project, there was a gateway/server running on a Raspberry Pi. There were a couple of sensor nodes and display nodes. The gateway and server communicated over MQTT, and all of the sensors and the display communicated over LoRaWAN. So now let's get into the second part of the presentation. Let's talk about some of the attacked surfaces. So there are two real things I wanted to attack here. I wanted to attack the software, and I wanted to attack the hardware. For the software, I want to exploit some software/configuration vulnerabilities and do some penetration testing. And then I want to exploit some inherent vulnerabilities of the hardware that we'll talk a bit more about later. So the first thing we did was to run the command nmap 192.168.1.1/24-A. This command will scan the subnet 192.168.1.1 with that subnet mask, and the -A option will scan aggressively. It will try and query any open ports to see what services are actually running on those ports. And so doing that, I've taken here the part of the output that deals with what appears to be a Raspberry Pi running ChirpStack. So we notice over here that port 22 is open, and SSH is running on that port, and we can see that that SSH version is for Raspbian, a Raspberry Pi operating system. We also see down here that port 8080 is open and running a ChirpStack application server that serves over HTTP. And we can work out that ChirpStack is a LoRa server stack that handles a bridge to the gateway as well as an application and network server. So that tells us that we probably have a IoT server running on a Raspberry Pi at this 192.168.1.120 IP address. So we will use that in just a second. The first thing we want to do is we want to get a list of ports commonly used by IP protocols. There's an nmap services file that contains a list of basically every port, as well as what are some common uses for that port, and also some information about what's the probability that that port is going to be used on any random machine. We don't really care about that now, we just care about what ports relate to, in this case, MQTT or CoAP. Those are both IoT communication protocols. And doing that, if we scan that file for lines containing MQTT or CoAP, we will get this list. And so I saved that in a file to be used by this command. So this command, we run nmap again, but now we say get the list of ports to scan from that list we got on the previous slide, and scan only this IP address since we're pretty sure that's what we're interested in. So when we do that, we will then find that port 1883 is open. Those other ports are all going to be closed, but port 1883 is open, and it looks like Mosquito version 1.5.7 is running. And then it gets some information from the sys topics here that are published by the Mosquito server. But it was kind of long, so I just didn't show those. It's not super important to what we're doing here. But so now we see that on this port, we have a Mosquito server running. So what we can do now is we can use the mosquito sub utility, and this is running on our machine that we're using to do this penetration testing. So we can use this mosquito sub utility and point it towards that IP address with that port and try and subscribe to this hash wildcard, which will subscribe to every topic. So I ran this command and then set up the system in a way that usual data would be flowing back and forth, as if it was in actual operation. And so I did that, and I let this command just run for a couple hours and saved all the output to a file. I then went through and looked for any interesting information in that file, and these 3 messages, all of these were just published as MQTT messages, and these are kind of cleaned up versions of those where it's a bit easier to read them. But we can see that these 3 messages were published. So we've got this first one, an application ID of 6. The name is IoT Security Project. The device name is left. We've got a device ID. We've got some information here, and we see that here is the message that was published. The same here, the same information, but with the right as device name and a different ID, as well as a device with the name of DISP with a different ID and some different data being published. So what we can do now is we can create a Python script that will exploit all of this. And so what this Python script will do is we will connect to the MQTT broker and then flood all of these relevant topics we know with messages. And what this is going to end up doing is overloading the gateway, and so it won't be able to function anymore. And then if the gateway can't function anymore, then the server isn't able to run, none of the LoRaWAN servers are able to work properly, and so the whole system will be brought down. So let's go ahead and go to a walkthrough of this denial of service script. This is a walkthrough of the denial of service script that we will use to run our denial of service attack against this server. So the basic idea here is that we will publish as many messages to all of the topics used by our server, both by ChirpStack and by the actual application. So the first thing we do is by examining all of the data we got from listening to everything that happened while the system was operating normally, we can work out that we should publish to topics like application/6/device, plus one of these 3 device IDs, and then the ending of the topic should be either RX or TX. Right? And we can publish all of those to our Raspberry Pi and port 1883. So then this for loop right here doesn't actually do anything, but it was useful. This just subscribes to all of these IDs to kind of reduce some of the noise whenever we send something to the server. And then we published a single message that was a valid message we got just from listening to everything, so we could see exactly what the server's response is. So we published this message, and we noticed that this is the server response. So if we wanted to control the display, which should be being controlled by the server, but we want to control it, this is what the server publishes, and it will publish it to the display's TX topic, or the transmit topic, and then ChirpStack will grab that and forward it to the display. Forward this data to the display. So we take a look at this data. It looks like it's base 64 encoded. So we can decode that, and then that will be spots 0 of 10. So then we can control the display by sending a message that looks very similar to this to the display's transmit topic. And so what we'll do is we'll create this display message, which looks exactly the same as this, except instead of this data, we will base 64 encode spots 10 of 10. And so it will always look like the parking lot is full. So now that we have that message, what we'll do is for every device ID and for every topic ending, if we are publishing to the display's ID, then we will publish this display message here. Otherwise, we will just publish this message right here, which is one of the messages that we got just by examining the normal output of the server. It's not actually very important what any of these fields are. This happens to be a valid message that would be picked up by ChirpStack. We already know that. And so we will just publish to this. And so this device name, device ID, address, all of this transmit info, all of these, none of these are actually very important. All that we really need to do is publish some message here so that our MQTT broker gets overloaded because it has too many messages to deal with. The ChirpStack server gets overloaded because there's too much to deal with, as well as the application server will also be overloaded because there's too much to deal with. And because we're sending all of these messages specifically to the display, if ChirpStack is able to do anything, the only message it should be able to grab is this spots 10 out of 10 message. And so there's no way for any legitimate information to get onto the display. We're filling it all with this illegitimate information. So that's the basic idea behind this denial of service script. So now that we know how our script is working, I want to walk through the demonstration I'm about to do of it. So in this demonstration, because the script is hosted on my desktop computer, it's on that virtual machine, I'm not able to run it in the same type of demonstration we did last time. So instead, what the demo is going to do is I will do a screen capture and show running the script from the virtual machine, and then what the effect that has. The way I'll demonstrate it is both with the application server. You'll see that that stops working and isn't able to run anymore, as well as actually the web interface for ChirpStack will also crash. And so this whole gateway will be brought down just because of this script is running. So let's go ahead and go to that demo. This is the demonstration video of the denial of service attack script. So as you can see right now, I'm in a virtual machine here, and I have the ChirpStack web interface open right here, right? And so we can see all of our devices are active. If we go into any device, we can see that it's publishing and receiving data. I just have the devices set up in a configuration where they'll just be constantly sending data. And we also have our server running over here. You can see that it's constantly sending and receiving data. So everything's working properly. Everything's working how we would expect it to. Then what I'm going to do is go in here and then recall that we have this denial of service attack script. And so what I can do is run this dos.py script. And if we take a look at what our server is now receiving, is there's now a whole bunch of messages, way more. Everything's happening at a much faster rate than it was before, because this denial of service script is publishing tons and tons of messages. If we go and take a look at the message queue for the display, we can see our message queue is now hundreds of messages long, right? And so all of this is happening, and what's going to eventually happen is there's going to be so much information thrown at this that the entire server is just going to overload and not be able to handle it. So let's see. Here's our server. Here's our application server. I've also SSH'd in over here, so we could run something like just editing a new text file, right? And that takes a second to start up. Going into insert mode. This is a test file. Oh, that's running a bit slow now. So we can kind of write that. Let's see, can we quit this? Yeah, we can sort of quit. We can kind of run clear. It's a bit slow. Let's exit and try an SSH. Oh, we can no longer type exit into our terminal here. There it goes. Okay, and we managed to get through that. And so that's the effect of this denial of service script, is it completely takes over the server and just makes it unable to respond to anything. So now that we've seen the software attack, I want to talk about the hardware attack. So the hardware I wanted to exploit here was these ultrasonic sensors that are used to tell whenever a vehicle is passing by each sensor. And so in order to do that, I want to talk a bit about how these sensors actually work. So the way these sensors work is you will send a certain sequence of pulses on the control pin, and then the sensor will send out a series of pulses and wait to receive a series of ultrasonic pulses, rather, and wait to receive the echoes of those pulses back. So the sound waves will go out, bounce off of something, come back, and the sensor will time how long did they take to come back, and then knowing the speed of sound and how long it took for the pulses to come back, it can work out how far away some device is. But these have a weakness in that all of them use the same sequence of pulses to send out. And so, if I take another ultrasonic sensor and just have it continually send out pulses, then I can jam up the sensor that's being used by the IoT system. And so I use that to create this jammer node. And all this is an Arduino hooked into another one of these ultrasonic sensors that has some firmware that just continually sends out pulses. It doesn't wait to listen back to see if it's getting anything, it's just continually sending them out. And so what that's going to do is that's going to make the sensors that are used by the IoT system operate unreliably. They won't really be able to tell how far away anything is because they're not receiving back the same pulses that they sent out. They're receiving back pulses that some other device has sent out. And so I'm going to go now to a walkthrough of this jammer firmware. This is a walkthrough of the jammer firmware. As you can tell, it's very, very simple. We're really not doing a whole lot here. We've connected our signal line to pin 8. We're not doing any sort of setup. We're setting that pin to an output, writing a low, letting that stay for 2 microseconds, writing high, let that stay for 5 microseconds, write it back low again, and then wait 5 microseconds before the next pulse. So what this will do is this is the signal to tell the ultrasonic sensor to send out a pulse. And then ordinarily what you would do is you would wait for that pulse to come back, measure the time difference between sending it out and waiting for it to get back, and that will tell you how far away whatever object the pulse is bouncing off of is. But in this case, because we're not trying to measure any distance, we're just sending out a bunch of pulses, any other sensors that happen to receive this pulse will then think that it is the pulse they sent out. And so with all of these pulses interfering, they won't be able to accurately determine the distance, and so these sensors trying to sense vehicles passing by will be unreliable. They won't be able to reliably sense a vehicle passing by because they're being interfered with by this jammer. So now that we know how the jammer is working, let's walk through how our demo setup is going to work. So I wasn't able to film this in my cul-de-sac, and so instead I have in my backyard just set up a simulation of how it should be working. So I've got a piece of plywood that if I point the sensors at it, it's at the appropriate distance where they will register that as a vehicle passing by the sensor. And if I point the sensors away from it, they won't pick up anything because they'll be registering something either out of range or too close. And so what I will do is I will first demo just that setup working by itself, and then I will go to a demo demonstrating how the jammer is going to work. So because this jammer is sending out multiple different pulses, when the sensors are pointing at the jammer, they won't be able to consistently pick up any data. They may sometimes register a vehicle entering or exiting, but as you'll see, if you compare between the explanation video of how the setup works and the demonstration of the jammer working, you'll see that the sensors won't be able to register at anywhere near the same update rate, and it's very random as to whether or not they'll actually register. In this case, whether they're looking at the piece of plywood, in the actual case, whether or not a vehicle has passed by with this jammer in the way. So let's go ahead and go first to a video demonstrating how this setup is working. So this is the demonstration video demonstrating how this setup is going to work, because I'm unable to film in my cul-de-sac right now. So what I have is, over on the left, I have just a piece of plywood that's simulating a vehicle. So if I point the sensors at that piece of plywood, it's at the right distance so that they will register that's a vehicle entering the parking lot and will send a message to the server accordingly. On my laptop here, I have the output of the server that's running on the Raspberry Pi on the rack gateway that's over in another part of my house. And then I also have these two sensors here. I have the left and right sensor you'll notice they're currently facing away from the wall, so they won't be sending any updates. But if you notice right here, there are currently 0 spots in the parking lot, 0 out of 10 spots full. And so I can take the right sensor and point it at that plywood, and it will begin to register vehicles entering the parking lot. And I can also take the left sensor and point it at the plywood, and it will begin to register vehicles leaving the parking lot. So that's how all these demos are going to work. If the left sensor is pointing at the plywood, it'll register vehicles leaving, the right sensor register vehicles entering, or in the case of both the software and hardware attacks, you won't be able to tell anything because the sensors won't be functional. Now let's go to a video demonstrating the operation of the jammer. So this is the demonstration video for the jammer. It's the same setup we had previously, where we've got the plywood, server output, and sensors, but now we also have, in addition, this jammer as well. So you can see there are currently no vehicles registered as being in the parking lot, and if I take this right sensor here and point it at the plywood, we should start to see vehicles entering the parking lot. And in fact, we do see one vehicle enter the parking lot. But we know the update rate of this, right? It should be fairly quick. In fact, we're already up to 3 vehicles in the parking lot, but it's not consistent. We're not able to consistently measure, yes, we've got a vehicle entering the parking lot. No, we don't have a vehicle entering the parking lot. Because this is just pointing at the wall, the update rate should be very, very, very clear. We should be guaranteed to register about 1 vehicle per second entering the parking lot. But we don't see that because of the way that this jammer is interfering with the sensor. So now that we've seen kind of 2 of the attacks that can be done on this system, I want to talk about some of the defense that you can do against it. For software, there's some mosquito authentication that's supported that can be used to defend against it. For the hardware, however, there's really not much you can do. If you're using these ultrasonic sensors, there's not a whole lot that can be done to mitigate this attack. Your only real option is to use different hardware. You may even need to use a different technology altogether. I'm not sure if there are other sensors, other ultrasonic sensors that don't suffer from this problem. I wasn't really able to find any. It seems to be a fairly common problem, even accidentally, that you can run into with these sensors. So there's not a whole lot you can do about that. But for the Mosquito server, Mosquito, especially in particular version 1.5.7, supports authentication. It's username password based authentication, and so every application that connects to the Mosquito server needs to have a username and password, and then you can set up per topic access control if you'd like, but I'm not doing that. I'm just disallowing all anonymous access, and so no anonymous, and by anonymous it means no application that doesn't have a valid username and password is allowed to even connect to the server. And so, since it's not even allowed to connect to the server, there's no way for it to send any sort of information to the MQTT server, because the MQTT server will just refuse to listen to it. And so now I'm going to go to a walkthrough demonstrating the effectiveness of this patch. So this is the demonstration of how enabling Mosquito authentication prevents the denial of service script from working. So we've gone ahead and enabled Mosquito authentication, and everything is now configured to use that. So if we go over here, we can see our server is running, and it's running just fine. If we go back to the ChirpStack dashboard, we can see we have a couple of messages queued for the display. That's just because the display isn't pulling down all those messages in time, because this is operating much faster than it would in actuality. But it's nowhere near how it was when the denial of service script is running. We can also see that we have some messages coming through, but they're not coming through with anything near the frequency they were when the denial of service script is running. This is much faster than it would be in real operation, but still not nearly as fast as that denial of service scenario. So let's go ahead and try and run our denial of service script again. So we've started running this script, and as you'll remember, before, it would immediately take over this server, and we wouldn't be able to see anything else. But if we look at it now, we don't see that. All the messages are coming in with about the same frequency as they were before. If we go and look at the queue here, I'll clear that. so that we only see new messages. You can see we're not immediately filling up the message queue to the display. So because we've enabled Mosquito authentication, our Mosquito broker is now denying access to that denial of service script. So it isn't able to publish the flood of messages it was able to publish beforehand. So now I just have a couple of closing remarks. There are a couple vulnerabilities that I didn't really explore here, but that are definitely present in this system. For example, I've changed some of the passwords, but not all of them. There's also the issue of LoRaWAN transmission. So all of these LoRaWAN packets that are sent over LoRa are all encrypted by default, but maybe there's some flaw in that encryption that you can explore and use that to sort of break all of this. Everything's encrypted using the application and network session keys, right? And as we talked about in the previous video, or in the previous presentation, we know that using application by personalization, there is a potential that those keys could be stolen off the device, or even stolen just by listening to the initial setup communications between the nodes and gateways. And so there may be a way to take those and use those to decrypt all of the transmission and then change and modify them. And also recall that I didn't implement any frame counting here. And so the system may be vulnerable to replay attacks, where you just capture one packet and just save whatever it was. You don't need to know anything about its contents. You just need to know, I've captured this packet and it is a valid packet because it was sent by the sensor to the gateway. You can then resend that packet yourself to the gateway, and the gateway has no way to know that that packet isn't coming from the sensor because it's just being sent over the air. And so it will receive that packet and perform that again. You could use that in order to take control of the system. I didn't really explore that very much. I just wanted to point out that's one of the possible vulnerabilities here. I also wanted to talk about some of the effects that these attacks could have on users or people who are parking in a parking lot monitored by this system. Because this system doesn't collect any personally identifying information, it only keeps track of the total number of vehicles in the parking lot, not any information about what vehicles or who's in those vehicles or who's in the parking lot. And so there's also no other information collected by it, right? And so there's not a whole lot of data that could be leaked by this system. If someone were to hack into it, you can't really do any sort of identity theft or blackmail or anything like that through this system's data. There's very few physical components of this system, and so it's not like something that has maybe a gate that opens and closes that you might be able to control to come down and break someone's windshield as they drive through the gate. You can't do anything like that. You can't really hurt anyone. You can't damage any property. With this system, there's no real major hardware components that are damageable. The things you could do is you could confuse anyone trying to park, right? You could display some other message on this display that should be about how many people are in the parking lot, but maybe you put up something yourself, or you could also cause someone to be late. So if you say that there are spaces available when there aren't any, or if you say that there are no spaces available when there are a few, you might cause someone who is relying on the availability of spaces in that parking lot and relying on the parking lot sensor to tell them whether or not anyone is in there. You might be able to mess up their schedule and cause them to maybe be late for something. Maybe you could cause them to be late to a presentation, maybe they're late to the tech symposium, maybe they're late to an exam, something like that. But that's about the extent of the effects these attacks can have on the users. So thank you very much for watching this presentation. I hope that all of your presentations go very well, and I hope that everyone has a good summer. Have a good day.